I'm not sure it is easy or not. Usually you don't need those. You use this way, you just use in terms of integral, n hat, right? So if you, this is E, okay. So that is this one, and you have, all right, so you do that, you expand, right? This is n minus 1. And this one, you definitely be able to get 0 because this one increase, and
right.
diagonal, yeah. So you can use this way, but then you don't need this one, right?
Okay.
If you use this one, just use that. And then that is, we just, the first is ask just ground state, right? So ground state, this one is also simple, right? The wave function. Let me see if we use, so that's chapter 4, one dimension harmonic oscillator. Here. That is this function, sin naught. Is that correct?
Right.
Yeah. So because this is the ground state.
Yeah.
The others is not complicated. You have all the others.
So
you just do the
okay.
direct to this.
It's just the perturbation of the ground state.
Yes, I think that's the
what
question,
it
right?
says.
Yeah. So you don't need the
I remember that. It's
Yeah.
Right here. The ground state. That's
Yeah.
part of what my question was. So
Yeah, you get more complicated if you go to not ground state. The function is more complicated.
Right.
So
Okay.
yeah, if you use it, I prefer if you already get this P4 is this operator if everything correct. I didn't check.
Yeah.
Then this is simple.
Okay. That's what I was thinking too, and I was trying to think how would the hint
Yeah.
be incorporated
Yeah.
in there.
Yeah, you don't need a copy because to solve the problem there are several ways.
Right.
If you do everything correctly, then okay.
Okay.
So this n is not, right? Is n 0, right? So that is, yeah. I think that, yeah. I mean, you just do, no. This n is any states.
Right,
But
any
ground
state.
state n is 0, right?
Yeah.
That is. Okay, if you think you need time, let's give you can turn. Either you want to turn to my mailbox this week or next Monday.
Next month.
I'm gonna try and get it to you this
Yeah.
week.
Yeah.
So that way.
Then I can, great for you. If next Monday, I definitely can grade and put it into your mailbox. Okay. All right. I want to discuss, finish the chapter 9 today. Is the vibrational principle. Then next Monday, at least we can cover the first or 2 sections about the about this time-dependent perturbation theory. Otherwise, we didn't cover enough topics. So that is basic. You are graduate student or take the quantum 1 and 2, but still not perturbation, but time-dependent and scatter, but we don't have scatter. Okay. Any others? Who others? Do you know where they are?
Jacob and
Okay, I'm going to stop it, maybe 5 minutes. So, remind, we introduced the vibrational methods, now we do the application. Oh, I just mentioned again, if I don't, just try to remind you. Next Monday, I'm going to give you the take home with that, and on May 1st, we will take in class at 1 p.m. All right. So remember, we want to find the ground state energy of the helium atom. The difficulty helium atom, we have 2 electrons. So if we have 2 electrons, you will see this term. This is an interaction between electron and electron. This term is, we cannot separate R1, R2 into integrals, so that makes difficulty. We already say that if you ignore this one, we got the energy compared with experiments, large difference. That means this one cannot be ignored, even cannot be treated as perturbation. So, but vibrational method we can do. So how to do that? First, we are going to find the trial function, right? So how to find trial function? We say we are going to use the physical intuition and the educated idea to guess what kind of the property of the trial function, right? So now the trial function, since it's ground state, that must, R1, R2, must have the basic property of ground states. But we know the ground state is like radial spherical, right? So that means at least it's kind of this, or let me do this. To maintain the basic, the ground state behavior is to be a kind of, if I'm going to say, 1, 0, 0, R1. That means first electron in the ground state, if it's a single, and multiply another electron and another R2, which also ground state. So that means because to maintain, right, the property of state of like single electron, right? Electron, that behavior first. So that's be something like this. But then, since we know this interaction, we have taken account. How to take into account? If we consider this one, we ignore this, right? So now we are going to take into account this one. Then physically, the effect of this is interaction between these two electrons is repulsive. So as an effect, the one of electron, the interaction between this electron and nuclear is weakened because this like the other electron has like a negative clock, right? That is like a screening effect, so that we call screening effect. That means to weaken the interaction between this electron and nuclear because there's another electron. And this weakening effect means the effective interaction between this one is weakened, right? So this the screening effect means that we are going to introduce the effect charge at nuclear. So that means the real charge is ZE, right? And then now we are going to introduce parameter at the Jazbo, which we can determine by variation. So that is idea means since ZE, if there's no any other electron, this is just interaction between ZE and E. But now, since we have another electron, that means this one should be, we know that Z plus should be smaller than Z, right? That is physical equation. So with these two together, so that means we are going to keep this one, but introduce or replace this by this. So the formula or the functions be like this. So we call this the trail function. R1, R2. Yes, now I'm going to write equal. Here I use the approximate equal, right? The formula same, but here R1 Z1. R2 Z1. So here, that is parameters we introduce. And compare it, okay, if you want to do that, then you have to be a right? That's different. So when we try to use this one, now this is a parameter we are going to optimize to see how much Z prime is, such that we can correctly or to characterize the effect of this one, right? So that is the idea. Now, when we have introduced this parameter to the trail function, so now we are going to rewrite the Hamiltonian in terms of Z prime, right? Since we are going to do the expectation value, right, between this, the Hamiltonian between these 12 states, right? So now we are going to rewrite Hamiltonian in terms of Z prime. How to do that? Let's rewrite. So now Hamiltonian is, let's rewrite the details. So now here, we have a kinetic energy, right? 2M. That is first particle, first electron, second electron. And now, the interaction between the electron and the proton, which we have ZE squared over R, right? But now I'm going to add a negative Z prime E square or R1, and plus A prime E square or R2. This is I negative, therefore I have plus, right? Plus, okay, the Z prime, the real one is this term, right? Right? The real one is, if there is no any interaction is between E and ZE, that is this term. But now I subtract this term, so I have add this term, just equivalent, right, to them. And then the remaining part is this interaction between electron. Okay, so now you can see this one only function the R1, this R1, this R2. So now we can rewrite H prime 1 plus H prime 2. When I say prime means now it is Z prime, not Z. But everything the same, like I did that. Then the plus, okay, this part. Let me just say term 3 plus term 4, right? Term 3, this one, term 4, this one. So, once we rewrite this one, now we can do this number 3, right? Number 4 step is now we are going to calculate expectation value of energy in Hamiltonian in these 12 states, right? So that is this one, 12. The denominator, if the normalize, this that's V1, right? So here, this one is normalized because, okay, because you know when we introduce the 12 function, which is this one, right? Here, this one. R1, Z prime, real, R2, Z prime. Okay, there's space here. 1, Z prime, R2, Z prime, right? And you know they are 1. And they are all non-normalized, right? So that is yes, indeed, it is equal to 1. So now I come to here. That is only we are going to do is do this integral. All right. So now, okay. Let me write again. So E is now Hamiltonian. We have 4 terms, right? So that means the first one is a 12 function for H prime 1, the expectation value, and the second one, expectation value of H prime 2. Then plus expectation value of, I'm going to 6 space, right? So I use term 3. And plus term 2. So that's 12, term 2, term 4. So we have 4 terms. Now let's look at the first 2 terms. The first 2 terms, it is simple. I'm going to use the, okay, use. So you see here, this one is the Hamiltonian first electron. And this 12 function is here, is a product of this. So when this one applied to the first one, it gives you the energy, right? Because it's eigenstates of this Hamiltonian H1 prime. So this one, and then they, okay, let me write down first. 1, 0, 0, R2, Z prime, 100, R1, Z prime, prime 1, 100, R1, Z prime, 100, R2, Z prime. So only this one, because H1 prime does not affect the R2, right? So this one is different energies. And then after this one is give us E1, one, and this thing, and then the remaining these two are normalized. So that is just the E1. Okay, this E1 is, I'm going to the E1 prime Z prime, right? And that is nothing but because it's on the ground state, n equal to 1, and L equal to 0, M equal to 0. So that is, you use just hydrogen lag item. That is this one. E naught is numbers. E naught is I just keep that. That's the ground state of the hydrogen, right? So that's just this one. Here, the Z prime come from hydrogen lag, remember? But now this is Z prime, not Z, right? So that since we have Z prime. Similarly, so now similarly equal to the second one. Because second one, first one, they have the same Hamiltonian. So the first two terms is not like this one. Now let's look at the third term. The third term is also easier because that is only depend on each individual R. So we can use third term, right? Term 3 is equal to, okay, let me first write down this, again, that is this first. So this, if, the two terms. Okay. 12. First one is Z prime minus Z E squared or R1, right? 12. And plus second one, 12. Z prime minus Z E or R2. Check, right? So you can see, let's look at the first one. The first one, 12, Z prime minus Z E squared over R1 is equal to, do the same thing here. The 12 is a product of the first ground state, first. So now this is R1, so I'm going to R2, Z prime, and psi 1, 0, 0. R1, Z prime. Now here this is a Z prime minus Z E squared over R1. Psi 1, 0, 0. R1, Z prime, and cat psi 1, 0, 0. R2, Z prime. And this one only works on R1. So we just do the interval for R1 and R2. These two are normalized, right? So that will not affect. And the first, this one, you see this is only radial part. The angle part does not depend on the angle, right? So this one, here. Okay. So that is, let's take the constant outside Z prime minus Z E squared. And then this is only the radial part R1, R1, 0. R1, Z prime, 1 over R1, R1, 0, R1, Z prime. That's all, right? And then here, you just use NL, 1 over R, NL in chapter 6, right? That's equal to 1 over n square a, okay. Since we have z prime, so I'm going to use z prime. That's this. Go to equation 682. So now finally, this term is equal to minus 2 z prime minus z e naught. Okay. So, and similarly equal to another term because they are symmetric. The 12 function for the second R2. Z prime minus z e square over R2. They are equal, right? Everything the same, only the replace. So in R2, this is R2 and R1 is normalized. The difficulty is the last one, term 4. Now let's work on term 4. And the details are integral, I will skip. I will post the details in my slides, a lot of details, several pages. I don't want to spend that time on the class, and we want to go to the physics. So here, I'm not going to post. So I'm going to just give you some of the key steps, and we know how to do that. So now we are going to deal with is this one, because this is this most difficult part is okay, is e square over r1 minus r2. This is number 4 term, right? Is term whatever this be term 3 or term 4, right? So that is. So this one. This one, let's first write down this. I take e square outside, right? So here the 12 functions say 1, 0, 0, r1, 1, and sorry, this is a cat, a bat, bra. So 1, 0, 0, r2, z prime, and then 1 over r1 minus r2. You see we can not separate. That is difficulty come from. And let's deal with R2. Do the first integral with R2 and then with R1. So we step by step. Okay, so now let's introduce this one as I. I is the function of R1, right? After integral with respect to R2 for this term, then we have that. Then we are going to do the integral between this R1. So now let's first look at this term. This term is, let me write that again, integral with respect to R2, right? 1 over R1, R2. Let's do this. So this one, the difficulty is that you can see it will also depend on the not only radial but also angle. Let me first write down here, and then you will see. So this 1, 0 is R10, R2, right? Z prime, and this the angle is a spherical harmonic y 0, 0, theta 2, prime 2, right? Then 1 over R1 minus R2 here. Theta 2. Now, this one depends on angle, theta 2. This is because, let me do it here. So now, since this integral with respect to the theta 2, now we are going to deal with this one in terms of theta 2. How to do that? Let's look, because this axis, the spherical coordinates is selected arbitrarily. We can select any direction as a z direction, right? So now, suppose this is R1, this is R2, and what is, this is theta 2. If we select, right? If we select R1 around the z axis, y, x, and y. So let's select the R1 along Z. In that case, then you will see here, this term is expressed in terms of this theta 2. Now, the radial part, let me just give you the very quickly. So that is, this part is 2 Z prime over A naught 3, and from 0 to infinite, 2 square, and this from the radial function, right? When A to 1, L to 0. So that is minus 2 Z prime R2 over A naught dr2. That is radial part. Now the angle part is from 0 to, for theta, right? Theta 2 is sine theta 2 d theta 2. And now this one we can use, so you see, where is, this is R1 minus R2, right? So we can use the law of cosine. This distance is this square of this square and minus 2 product of this, right? Remember that. So that is square root R1 square plus R2 square minus 2 R1 R2 cosine theta 2. And for the another angle is phi is from 0 to 2 pi, but no any function depending on, so that can be integral, it's a 2 pi, right? So that is, okay, I think I already, that is to sort of have to make it 2 pi. Then after that you can see. So now let's deal with this term. So this term is a bit complicated. After that we can do this, right? So now let's define x is cosine theta 2, right? If you do that, then this term. So now from 0 to pi sine theta 2 d theta 2 R1 square plus R2 square minus 2 R1 R2 cosine theta 2 is written in from minus 1 to 1. If x, then theta equal to 0 is 1. Then theta equal to pi is minus 1. And then when you do that, you will see there's another negative sign, so that just changes it. And then here is dx R1 square plus R2 square minus 2 R1 R2x. Right? And to this integral, because these are constant, so like this square root A something. So I think this one very easily, and just give you the result because otherwise it's minus 1 R1 R2 square root 1 R1 square plus R2 square minus R1 R2 2R1 R2x with x minus 1 to 1. And finally, when you substitute it to those numbers, you will see finally it becomes simple. 2 over R1 when R1 is larger than R2. And the 2 over R2 when R1 is smaller than R2. So we have separate two regions. Now this one, this is this part, right? So this part like this. Now we are going to integrate with R2 from 0 to infinite. Then we have a separate from 0 to R1 and from R1 to infinite. Right? So now I'm going to continue, use that result. We will have, let me just give you 2 Z prime over A naught Q. First is from 0 to R1 and R2 square exponential minus 2 exponential minus 2z1 R2 over A naught 2 over R1 dr2 plus from R1 to infinite R2 square exponential minus 2z prime R2 over A naught and 2 over R2 in R2. Those we have used the integration by part, so the details I will skip. Then now I give you a final result, 1 over R1, 1 minus 1 plus Z prime R1 over A naught, and not the exponential, minus 2 Z prime R1 over A naught. Okay, that is here, the I, as a function R1, right? So once we have those, we are going to do the second integral. You already wrote down the numbers. So finally now substitute this one into here, right? So we are going to do the integral with R1. But now it becomes simple. This here no angles. Right? So now this one, when we go to the second integral with respect to R1, is only radial part. The angle part is normalized. So here we have 12 function of square over R1 minus R2 is, let me just write down first again, H1 I R1 Z1, and that is, as I said, because this function only depends on the radial, so the only part is E squared take outside to the R10, R1, Z1, I, R1, R10, R1, Z1. That's all. And okay, another R1. If you do not remember, I just write it down. This again, so you know how to do that. Infinite. So that this 2R1 radial function is 2 Z prime over A naught 3 over 2 squared, right? Because 2 and then the I. Then we just use here. Exponential, sorry. Exponential function. Exponential here. Minus 2 Z prime R1 over A naught and R1. I R1. R squared here. So R1 squared R1, right? That's the radial integral, right? And the remaining all are radial integration by parts. So now finally, I give you a result is very simple. That is. So we obtained all the integral. Now we are going to sum all together the total energy. Then we are going to apply the, variational means try to optimize Z prime such that energy, the variation of energy is 0, right? So now the total energy here is a function of Z prime, right? Which is we define, which is we introduce the trail function and the Hamiltonian. The expectation value of Hamilton and this trail function. Now remember the first two terms is a single electron, so we have 2 times Z prime square E naught, right? That is 2 per. Says the third part is we already integral, so I give you the result is also each one is 2, so that's what 2 to 1 4 Z prime minus Z E naught. That is the third term and the fourth term here, right? Minus 5 over 4 Z prime E naught. So that you see this is a function Z prime. Now let's take the Z prime square together and then let's finally, so I'm going to rewrite this as minus 2 Z prime square plus 27 over 4 Z prime. That is energized function Z prime. Now, variation method means let's.
Can you read the bottom one?
Sorry?
The bottom one? Can you read that?
Okay. That's too fast, right? Okay.
No, it's
It's a bit. All right, so now we are going to see by var read 1 equal to 0 over partial, so same thing, right? Partial z prime, factor e partial z prime equal to 0 to find what is the optimized z prime. So then this one is very simple, right? So when you do the partial e with partial z, you have 4, negative 4 z prime, and then this is a constant, right? So we have minus 4 z prime plus 27 over 4 e naught equal to 0. So we can get z prime. Now I'm going to use star here. That is optimized, right? So that is by solving this one is very simple. 1.6 is definitely smaller than 2. Consistent with our initial physical or educated understand that the screening effect will weaken the interaction between the nuclear and electron. So initially, the nuclear will have 2 electrons, so that Z is 2, right? But now, due to the screening effect, the effective Z is less than 2. So now with this one, so let's see the ground energy, right? The E prime now optimized with Z star prime, right? This energy, let's see. That's be give us, so what the numbers? It is, you just substitute to here, right? And then you have, okay, if I write that here, so since this is the first term, plus 27.4 Z star prime, E naught. Now can I release this column?
Yes.
Okay. And that is, that substitute Z star prime, then we can have these numbers. Minus 77 electron volt. Remember experiment, so the theory, how did the accuracy. For accuracy, we use this version method. Now let's see this theoretical result, minus experiment, minus 78, right? 0.975. Divided by experiment, right? 78, 975. That is multiply 100%, but how many percentage? It is about 1.87%. Very good, right? Less than 2%, the difference. So you can see how powerful the vibrational method to improve this ground state entry for the hydrogen for this helium atom. This one example is, you can see we have better the trail function. If the trail function is very close to the real ground state, you will have a very good result. But question is, to construct the trail function is difficult. We need the physical intuition. But if consider we have a very complex system, how can we have that idea? So now for general, we are going to introduce another very general method. Is called Rayleigh-Ridge method. Rayleigh-Ridge method. This method means how to construct trail function. So it's a trail function. So okay, the trail function is a we can construct trail function by linear combination with I from 1 to n ci by I. Now I'm going to explain each individual. So now here is note first n was a finite number. That means you here in principle, if it extends in infinite, that will more the n bigger, the more accurate because include more information. But if as practical to do the computation, infinite is too much, right? In terms of the memory and also the calculation CPU. So usually here it's up to you how much you can see, up to where you can increase by 1, 2, 3 until you see the accuracy is better. So that is finite first. Then here, this side is the basic side. basis set means it's which is independent, right? Now, the basis set we have independent, that means, and here for finite, right? For finite, and that means this is not complete basis set. Complete basis set. That's fine. Don't worry. Otherwise, it is in principle when we, as we computationists, we know to cut software. It's up to you. Here is also we call it criteria, energy criteria. How much you are going to cut, and then you are going to study your system and compare with existing experiment with known value, right? So then you can judge how much it is enough. Then you are going to use this to calculate the other system, unknown system, right? So this is the first issue. Second one, you have several issues. 1, 2, 3 here. This orthogonal or may not orthogonal. So the inner product between these two bases is either orthogonal, so that is delta function orthogonal, or let me use SI this overlap. Now orthogonal. Both are okay. We didn't require is must orthogonal. Even not orthogonal, so we can have this one we call the overlap. That means overlap between the orbitals or the basis function, right? So that is flexible when you select this basis. Now, which kind of basis you are going to select is up to you. So to select this one is also arbitrary. Means you can either use plane wave. Plane waves is the simplest, right? Plane waves. Like exponential ik dot r I minus something like this, or atomic orbit, which we obtain like hydrogen-like atoms. We have already the formula of atomic orbit in the spherical coordinate orbitals. For example, like psi n l m, right? Or Gaussian type. So in the quantum chemistry, they use Gaussian because that is easier to integrate. Gaussian orbitals. So when the people say that which basis set you are going to use, or this code, like Gaussian code, they use Gaussian orbitals. Now in our case, our group use VASP code, use plane wave. And we developed like semi-pure method, we use atomic orbit. So this one localized. So those are either to describe the molecules' localized behavior. This one to the bulk or infinite sheet, right? Infinite dimension, then you can use the plane wave. But when you deal with the surface, there's a jump from the surface to the vacuum. So that is a lot of technique to which one you are going to select. So here, that gives you some idea. Anyway, you can develop. Okay, and then here, number 5, Ci, right? So here, we have the coefficient Ci. These are adjustable parameters. Like we introduced 12 function, we introduce a lot of adjustable parameters to adjust, optimize, right? Adjustable parameters. That is the each different system, this parameter different. So that control how accurate for the specific system. Okay, that is the idea. And once we have the 12 function like this, now we go to the apply the variational method. You will see the question will reduce to solve this matrix like eigenvalue problem. So now let's do that. Okay, I didn't. This is a parameter method I may require. The normalize, that may be very fundamental, right? So we also require this trivial functions be normalized. That means you adjust this one also to satisfy this. So once we have this, now, okay, I need that part is giving me the more information. So normalize means the trivial function will have like this. Summation I from 1 to n, summation j from 1 to n, ci star cj, right? And then this one is I j. Now since this one either orthogonal or non-orthogonal, so there are two results. Okay, so one is still keep here. I from 1 to n, ci star cj. That is orthogonal for this case, or non-orthogonal if we select non-orthogonal orbital like the atomic orbit, that or Gaussian usually is non-orthogonal. Ci star cj Sij. So here we have overlap. Okay. Now those is required for this trivial function. Now we go to calculate this one, right? Expectation value, we're going to apply the variational method first, calculate expectation value for energy and this trivial function, then to do the variation to find the optimize the numbers, right? So that is, since here we already normalized, so that is only this term. No, the denominator already equal to 1, right? So that is this one. Okay. Now suppose this is I think I write down this one, it's too simple so now. This is okay. I'll do this one. That is E trivial. So now I'm going to apply, right? So now we are going to apply the variation. Apply variation method principle. So we are going to vary the left-hand side E trivial equal to variation of the right-hand side. Right. The left-hand side here, left-hand side is variational E, and make this, I think I need to take this part. Variational E with keep this trivial function, do not vary, and plus E and varies this integral, right? And left-hand side, right-hand side keep. So this one, since this is integral, so the variation is 0, right? This one is 0. So the left-hand side is only variation of E is this. That's equal to the left-hand side is variational, the expectation value of Hamiltonian. So I move the right-hand side to the left-hand side. That means it's variation of this integral minus equivalent, right? Minus E equal to 0. Since we assume we are going to make this equal to 0, right? So now this one. Now we are going to or like this, since this is or like H minus E. Which is the integral of the Hamiltonian matrix energy if we want to, this we are going to obtain. Do this. Now we are going to substitute this trail function. It's here, right? So that is trail function. And this one. So we substitute into the bra and the cat. This is became to the variation of, since it's two integrals, I from 1 to n, j from 1 to n, right? And ci star cj. Now this matrix element ij minus e. Let's consider more general case. If non-orthogonal. If orthogonal, this one is always 1. Right, so that is 1. And that's equal to 0, right? We are going to do this. Okay. If I say that is I, so that means delta I is equal to 0. That is equal to partial I, partial any coefficient C I star should be 0, right? And I from 1 to all the coefficient. Then this one, you see here, when you do this, this one disappears, right? So now you have reduced to summation j from 1 to n cj, and then the hij minus esij equal to 0. So familiar with those? So you can see j, but here I from 1 to n. So for each given I, we will have a linear equation, right? This linear equation to solve this one. This is unknown, right? Those one gave us the basis, we know those matrix elements. So we are going to solve this. How many? We have n linear equation. And this n linear equation is, like in the matrix representation, is a matrix, right? It's an n by n matrix. Let's go to H11 minus ES11, H12 minus ES12. Okay, and HNN minus ESN, NN. And so HNN minus E, N1. N1 minus ESN1 until HNN, so this is S1N minus ESN equal to 0. Sorry. There's also coefficient here. That is matrix here. And then C1, C2, Cn. Right? So it became solve this eigenvalue problem. We call in simple, in the notation is like this. H is matrix now. I do not have hat, right? Because it's matrix. Es also matrix, and C equal to 0, or HC equal to ESC. This we call generalized matrix eigenvalue problem. Generalized eigenvalue problems. So now you see this trail function and this technique is now reduced to solve this, and we familiar with those. And how many? This n by n depends on how much basis size you are going to select. The bigger, you will have a bigger matrix. The smaller, but of course smaller, maybe the accuracy is less. The more you include, the accuracy is more increase. So now the solution to have the non-zero C is found this determinant of this, right? That's for solution required solutions for non-zero Cj is the determinant of this equal to 0, right? That is always familiar. And so now this question is reduced to solve this. So from here we have a series solution, also called eigenvalues. That is eigenvalues for the system, how many allowed eigenvalues or different levels, but we solve those and each one. So what you are going to do is select the basis set and construct your function. So you are going to just calculate the matrix element of Hamiltonian and overlap. Then build up the matrix, solve this, right? So for C, you just solve this. Once we have E, I, right? C, if you say Ci, and then now this I is C1, okay, then just this one to distinguish this C2I, C and I. Correspond to one I eigenvalues, you will have eigenstates, right? Those are chapter 2. We know how to do that. So basically, we solve. That is the basic, the computational physics, what we do, that is. So you will see different type of this, the computational code based on the quantum mechanics. They are how to deal with the potential, how to select the basis set, and they all select those to solve this generalized eigenvalue problem and find the energy or eigenvalues from states. We have a little time. I just give you one example. See how we apply this. I think Zan asked me a long time ago, say how about this molecule, the bond length, right? Now this we are going to give you some idea. What's the form of the bond length? So now the example is ionized hydrogen molecule. So that is a hydrogen molecule. I. What that means, we have two hydrogen molecules, have two hydrogen atoms, two electrons. But if one of the electron ionized, only one electron, two nuclear. So that is easy to prove, to treat, right? But of course, now every system you can do. So this case, you know that is here we have one is proton, another proton here, and suppose we have one electron here. So now this is suppose now I'm going to give a coordinate. This is a capital R1. Is where the nuclear. This is the origin of the coordinates. And this is a capital R2, which is the second nuclear. And then this distance is R. Let's see. Okay, here, this is R, right? This is R of the position electron. So this distance, R minus R is R minus R2, right? And this distance is R. The distance between two nuclear we call the capital R12. And that gives us a boundless. How this the two hydrogen atoms stabilize, form the bond, what's the condition, right? So now let's write down first Hamiltonian. Hamiltonian, we have the kinetic energy of the electron. Let's use this. So that is electron, right? And then the interaction between electron and nuclear, we have two, right? So that is attractive. Okay, 1 over R minus R1 plus 1 over R minus R2, capital R2, right? And then here, we also need the interaction between the two nuclear. That is repulsive. Capital R1 minus R2. Okay, so those are the terms or potential, inactive potential in the Hamiltonian. Now we are going to select the trail function. Trail function we are going to select, since this one is like atom, right? Molecule. It's more localized. So gravity is not good set, basis set. We are going to select atomic orbital as the basis set. Since the idea is, since if electron move around this one of nuclear is like hydrogen atom, so that orbital follow this hydrogen the atomic orbital. From here is another one. So that's the linear combination of the two, right? So that is the idea. That is the linear combination. I from 1, 2, there are 2 nuclei, right? And each one has n, l, m, the quantum number. Then the coefficient Ci, n, l, m, and this atomic orbit, right? That is for hydrogen atom. But now the center is from r minus capital R, right? Each one. Even center here, so linear combination is. So this is the one of basis set we select. Now the question is how much, as I said, n, to where you're going to come. It's up to you. So this is this one is selectable. So now let's select the simple case, or the simplest case is n equal to 1, from the lowest, right? L and m equal to 0. So now the trail function is okay. The first one is C100 because n equal to 1, right? And psi 100 when r around is capital R1 plus C1002. Another orbital is r located around R2, right? Just these two. Of course, this is simple. You will see the accuracy is not good, but we just give you an example. So to make this simple, I do not want to spend time to write, so I'm going to say C1, say 1, R plus C2, say 2, R. I just make a simple expression. So now, okay, we are going to find this, right? We are going to calculate the matrix element. Then we are going to solve the generalized eigenvalue problem. So first step, you select the basis. First one is Hamiltonian. Second one, you can select this. So number 3, we are going to calculate the matrix element, right? Matrix element Hamiltonian. H11 is psi 1, H psi 1, right? Okay. And here, H I already write down here, so to save time, I think I have only 2 minutes. So now let me just give you a final result. The final result is E1 S11 plus 2D11. I'm going to give you what this means. Sum of term we just simplify. S11. And we give a name as I11. So E1 is the ground state of this item. Okay. So here, S11 is overlap, right? So that is here is we call this, in this case 1 is called overlap. And D11 is defined as A naught, so 100 R minus R1 1 over R minus R2 psi 100 R minus R2. So you see the integral is between R1 and R2, and we call this one is the right integral. Details formula I will give you in the slides I will post on the Blackboard. So just give you the notation. That is H11 and H12. Second matrix element H12 is Z1, Z2, right? And the result is here. E1 S12 plus 2x12 minus 2A0 over R1 minus R2. You see those functions are all functions of capital R, right? So that is the, after integral, the lower R also disappeared, right? So then here S12, which I give the name is I12. Here S12 is the overlap between Z1. Z2 is an overlap. And then this we have, in addition to, yeah, here we have X12 here. X12 is Z1, 1 over R minus R2, Z2. Here we code D here, okay, D is, I think I made D is correct, right? R2 is. This one, D is here, is between the same, yeah, that's a mistake. That is so-called divided between the same R minus R1, but here is a cross between this R1, R2, so that one, yes, that's be 1, 1, right? Set 1, set 1. So this code exchange integral, since between two center of the nucleus. This one is between 1, right? Only between this and the integral, between this integral. Another one is between this and this, so it's called exchange. Set 1, set 2. H21 is set 2, H set 1. Again, we will have exchange integral because between the two centers, right? So now, let me give you the result. It is equal to E1 S21 plus 2x21 minus 2A0 over R1 minus R2 S21. Let's give a name I21. So here again, S21 is overlap, and X21 is also another exchange integral between the Z2 and Z1. Is Z2 and 1 over R minus R2 Z1. Now we will have the last one, H22. Then we can calculate, this is a 2 by 2 since we have only 2 functions, right? So that's a 2 by 2 matrix. That is the simplest case. H22 is Z2, H Z2, right? Between this, the center of the second nucleus. And the result is E1 S22 plus 2D22. You see this is direct because between the two function is same center, right? 2A0 over cat R1 minus cat R2 S22. Also give a name I22. Similarly, the S22 is the overlap between this Z2 and the D22 is another direct integral of 1 over R minus R1. In this case, 2 and R1, right? Z2. Okay, so now we have this. So see, I have nothing. I don't have time. So
Are you doing a 2 by 2 integral because
yes,
there's two
basics? Yeah, two basic function, right?
Right.
So then we'll build up a 2 by 2 matrix. So now let's solve this matrix, and you will see the result. We will have the bonding and the bonding states. So now we are going to have H is I1 1 plus actually here. I12, I21, I22. And S is 1, S1. Here S is just okay. Let me just do this. It's simply another representation here. 1, 2, 2, 1. Here I1 is equal to I11 and I22. I2 is I1. You will see they are same. And S11 equal to S22 equal to 1. S12 equal to S21 equal to S. We introduce. So that is by this introduced, then we have this 2 by 2 matrix. So we are going to solve first, find the eigenvalue problem, right? We are going to do this determinant of H minus E S equal to 0. So that is I1 minus E, and here is I2 minus ES, I2 minus ES, and I1 minus E equal to 0, right? So solve this one. It's simple. So now we have E. We have two values. E equal to I1 minus plus I2 divided by 1 minus plus S. Which one is here I already defined I1, I2, right? So then each one I already have here. So now you can see energy has two terms, and these two terms now, if I substitute these details, you will find it is equal to the two values. One is E1 plus this term, and plus 2E1 plus 2E1 multiplied D. Okay, I also have the D divided by later on D11, D22. Yes, yeah. Also let's see. D11 equal to D22 equal to D, and X12, X21 equal to X. So here is a B plus 2X divided by 1 plus S. Another is E1 plus E0 over 1 minus 2 plus 2E1, but here is E minus 2X and denominator 1 minus S. So those are function, they are function R, right? Because you can see each term after integral is function R. R is the difference between R1 and R2. So if we define R is the difference between R1 and R2, that is difference distance between the two nuclei. Then you will see here as a function R, I have an E1, E, I usually say E symmetric or E antisymmetric. So you will see here, this is a function of E symmetric. And here we have a minimum here. This is R naught, and we say that is bound. Right, so that is, we call this a bounding, we call it forming bound, bounding state. Another is EA. This is a EA, which is anti-bounding. So when the people say bounding, anti-bounding, is this. Then we have two the nuclear or molecule, they interact each other. So they perform to go together, but this interaction between the nuclear and the electron, the attractive and the repulsive combine together. So finally, if they go to this state, that is stabilized. And this stabilized is these two nuclei form the bond. So that if the nuclear away, they try to go back, right? So if two go back, try to run away. So that is this equilibrium states. Okay, so here, just give you accuracy. So the accuracy, how much, you say that is so simple, accuracy. The experiment E bound, this we call this is E bound. The bonding energy is the energy of this combined system corresponds to two infinite separate, right? The bonding energy is experimentally is 2.79, but this calculation theory is 1.77 eV. So you see this still not good accurate, and the bond lengths are not. Experiment is 1.06. If you go to this, you can find anywhere the hydrogen molecule from the bond, right? Hydrogen bond between two, and the theory is 1.319. How to improve? Increase the basis size. So, for example, now we only include 2. Let's include 4. Another 2 is from this. We include those one, right? Let's include this one. So we have 2, 1, 0 around R1, capital R1, capital R2, and another. Then you will see you will improve. So that is why we increase more basis and you will have more accurate result. I just use 1 minute. So now let's give you the wave function also looks like. So for bound states, you are going to solve this CG, right? Go to this one. And get the function that is looks like, which will be so called symmetric. Is a side view is like this. Is R1, R2, and we have the wave function like this. So this one is overlap. Or this is side view or top view you will see. This is symmetry. Okay, top, side. And for antibonding state, this looks like side view is just opposite. This is a side, and top is like here, 2 nuclei here, and each one is and less overlap. All right. The lot of details is if you're interested in the computational simulation, you can go to the details. I'm going to post those formulas, a lot of several pages, give you so you know where it come from. Yeah, that is now the basic starting point from the computational calculation to deal with the many particle system. All right, so now we have only one class next Monday. I'm going to introduce the time increment, the perturbation, and the picture. The picture in quantum mechanics, Schrödinger picture, Heisenberg picture, and interaction picture. Give you some idea about this knowledge. As I mentioned, the homework, if you finish, you can turn today. If not, either if you can finish before this weekend, put into my mailbox, or next Monday, right? Next Monday, the last day, so I'm going to give you this final exam take at home, and then yes, thank you. And then May 1st, we are going to have this in-class final exam. All right, you have another class, right? So, let me ask you, I know this time, most time I spent in last semester, chapter 2 about this mathematical tool. Do you think that is necessary? To save time, I can comprise that chapter, but I think that chapter is also very important, right?
I think it's an important chapter. I think when Dr. Janthius taught math methods, that people may have seen more
Uh-huh.
than when we took it when she was on sabbatical.
Okay.
So maybe it won't be as important to spend as much time on in the
She will
future.
cover some of them, right?
I think so. They could
It's
probably
the same
speak
year,
more.
same semester, right?
I had
You let them ask
Yeah,
them. You
yeah.
took the Dr. Janti last fall, right? The same time we quantum one. So you think, I mean, not for you. Next new student come, you think I can comprise the chapter 2 with
I
me?
feel like maybe just a summary of all
Okay.
the different tools.
Okay, do not explain where what's the details, right?
Yeah.
Okay. Yeah, that will save time.
They'll
Yeah.
get really good at it when we do your midterm.
Right,
They'll know eigenvalues, the eigenstates inside of that.
Yeah, and also your qualified exam help you, right? This one also, right? So those are really important. Do some practice. Okay, thank you for your feedback. See you Monday.
Thank you.
Is it recording?
Yeah, yeah. That's fine. Thank you.